decay to the minus 70 seconds. So no stable element beyond for A is equal to 5 or 8 x. So nuclear synthesis end here. Now, what is the way out? Fusion of 3 alpha to form 2 helium to form carbon. First proposed solution was triple collisions. So, but the rate of this triple collision is very rare. So, how to proceed? So, Salpeter proposed that carbon can be produced through sequential two-step process where alpha and alpha fuses to produce the beryllium 8, and this beryllium within this lifetime of beryllium, within this lifetime, if another alpha comes and captured, so forming the 12 carbon by the triple alpha reaction. So this is a non-resonant sequential process, but non-resonant process. So the non-resonant capture process was not sufficient to explain the observed abundance of carbon on the Earth. So Fred Hoyle predicted that the reaction rate may enhance if a resonance occurs at the formation threshold of alpha plus beryllium 8. So problem, there is no known energy level of carbon around the Hoyle's predicted energy level. So it was experimentally observed that in beta decay boron 12, a state near 7.65 MeV with a 0 plus state, and this is known as the Hoyle state, and this is 380 keV above the 3 alpha decay threshold and 290 keV above the beryllium 8 plus alpha decay threshold. So Hoyle state puzzle, the Hoyle state is the second Hoyle state is a second 0.2 plus resonant excited state of carbon at an excitation energy of 7.654 MeV, plays an important role to understand a variety of problems of nuclear astrophysics like elemental abundance in the universe as well as the stellar nucleosynthesis process as a whole. The structure of this state is very exotic. There are many unanswered questions regarding the configuration of this state. This state was not cell model is not able to explain the state, and it is predicted to be a 3 alpha cluster system. If it is a 3 alpha cluster system, then what is the configuration of this alpha? Whether it is a linear chain where all the 3 alpha are like this, or it is a loosely coupled 3 alpha cluster gas-like state DD5, and or it is a 3 alpha cluster condensate in the lower s orbit DDE with all equal energy. So how to visualize experimentally? So one studied the decay of the Hoyle state. 5 minutes. So it will decay by 2 modes. With the Hoyle state, one is direct decay, where carbon will decay into 3 alpha directly, or a sequential decay process via 2-body intermediate, which proceeds via 2-body intermediate configuration. One carbon will decay into beryllium 8 plus alpha, and this beryllium 8 will decay into alpha plus alpha. That is, final result is only 3 alpha. Though apparently this direct decay is insignificant, but important from both astrophysics and nuclear structure point of view. So you see the reaction rate, most of the time it is, till now this is assumed there is no direct 3 alpha decay. So reaction rate is only for the sequential decay, and it will govern by the width of the radiative decay. So however, if there is any 3 alpha decay mode, then this gamma alpha 0 by gamma will be less than 1, and reaction rate of sequential direct will be less than R sequential. That means there will be reduction in the carbon formation, and it will modify the elemental abundance. So direct decay has a strong role in elemental abundance. So one has to measure it very precisely. So we did an experiment at VCC using carbon 12 using carbon 12 tarbate and alpha 60 MMAP alpha beam, and we have detected all. We have did a complete kinematical experiment. So where we detected all the 3 decay alpha particle along with elastically scattered alpha particle. Total events, this is the experimental setup, and total events were detected was 1.6 into 10 to the power 5 events. So the present high precision nearly 0. So this is the symmetric its plot for various decay mechanism of the oil state, and this is the sequential decay. Most of the this is the experimentally observed sequential type of decay. So this is DDL type decay, this is DDE type decay, and this is DD5 type decay. So most of the time it has been found that it is decaying through sequential decay only. So we have convert the present high precision nearly 0 ground experimental study with 1.6 into the for 5 oil event has converged on upper limit for the direct decay at 0.019% with 95% confidence limit, which is more than a factor of 2 lower than the limit obtained in the earlier studies. These have been published in Physics Let Us Be. Now, very recently we did another experiment, but just in March we completed the experiment, study of gamma decay of the Hull state. You see, this gamma decay we have measured in coincidence with these 2 gammas in coincidence with elastically scattered proton. And the main motivation was that because previous measurements showed that gamma radiation, this width for the gamma radiation by total was 4.13 to 10 to the power minus 4. But very recently with modern apparatus, it has been shown that this value is changing, 6.2 to 10 to the power minus 4, 30% higher rate. So if it is so we wanted to verify these results with a higher precision measurement. So we have done this, completed this experiment, and analysis is going on. Hopefully we'll get some good results for this experiment also. So in summary, substantial amount of very high quality work has been done using PEC in last 4 decades, particularly in the last 2 decades. It was possible due to the creation of excellent facilities for the utilization of the machine. The synergy of excellent in-house team of experimentalists and theoreticians was key to above success. With the possibility of variety of heavy iron beams in near future, we will be able to do more exotic surveys in the coming days. Thank you.
Vandana, the talk is open for discussion questions. Questions, comments? Well, if not, let's thank Dr. Chandana Bhattacharya.
It is a very nice presentation that a lot of experimental setups has been created here, and Mrs. Purnima probably is scientific officer. He has sold a small superconductor and a trap, and she has shown me, I was very pleased to see. One thing I just want to share. Once I was retired from NDPC as a GM. Now I used to take classes for the EDs. Now what I was doing, I used to read the slides. I didn't take any preparation for that before. There was a class, I just shared my experience. There was a class of presentation skill at PMI, Delhi. That faculty told that please have a preparation beforehand, good preparation you take, and you just tell the gist of the problem and make an eye contact with the spectator. I am just sharing my what he has told. Eye contact with the coordinator, take what the reactions is there, and don't tell too much. You just see the gist of your things.
I think we don't have much time.
Thank you very much. It is a very good presentation.
Yeah. Thank you very much, Chandana, once again. The last talk of the session is by Dr. Navanita Noshka. Let's greet her in the meantime. Please present the leader. Welcome.
This is a bit scary. Anyway, my talk is about high energy accelerators, one-stop solution for exotic radioisotopes of multiple uses, from therapy to neutrino mass measurement. First of all, I am very thankful for this platform to Professor Sinha, who gave this opportunity as a youngster, and I'm very grateful to my mentor, Professor Lahiri, for allowing me to give this talk. In fact, this talk is on his behalf. Okay, so I'll go straight back to 1935, when the stage was ready. There was Becquerel, there was Pierre Curie, there was Madame Curie, there was Einstein and all the stalwarts. But there was still no show from any of the technologies like vacuum technology or cyclotron or reactor. Still, the Nobel Prize in Chemistry was awarded jointly to Frederick Joliot and Irene Joliot Curie in recognition of their synthesis of the new radioactive isotope. Since then, artificial radionuclides are working for life and humanity. So if I'm talking about radioisotopes for nuclear purpose or nuclear medicine, then I must go through the stages of growth phases in nuclear medicine. The first growth phase is obviously the foundation laid by Madame Curie by the discovery of radium, and after which it was the Radium Institute. Radium was used for various purposes, for medical purposes, and then the second growth phase followed the evolvement of the radioisotopes as the diagnostic tool. It was the discovery of radiotracer technique in 1913 by George de Hevesy. The third growth phase is rather the accelerated one, and it is in recognition when the scientists were trying to use the radioisotopes for both therapeutic and diagnostic purposes. And there was the discovery of cyclotron reactors, and as you may know, 99M technetium, which is one of the most magical radioisotope for diagnostic as a diagnostic tool. The present growth phase is about the concept of theranostic, where we, the scientists, are trying to progress with the concept of therapeutic and diagnostic. So it is basically an amalgamation, the conjugation of therapeutic and diagnostic radioisotope, which can be directed for a particular clinical application. So from where and how? Yes, of course, there are nuclear reactors from which we can get some of the radioisotopes, especially 99M technetium, which is absolutely a nuclear reactor candidate. But if I talk about some others, then they can be produced by proton-induced reaction or alpha-induced reaction. Now, I told you about the growth phases. If I now talk about the radioisotopes, if I distinguish between the radioisotopes, then there can be radioisotopes in diagnosis, there can be radioisotopes for therapeutic purpose and also for theranostic purpose. So if I am talking about diagnostic radioisotopes, then there can be 99M technetium, which is very common. Apart from that, 67 gallium, 66 gallium, which can be used for SPECT or PICT. Apart from that, if I am talking about therapeutic radioisotopes, then targeted alpha therapy can be done by 2,1,1 astatine. Targeted beta therapy can be done by radioisotopes like 67 copper, 76 arsenic, whereas if I talk about the theranostic radioisotopes, which is at present one of the in the limelight, then I have given some of the examples like 43, 44 scandium or 47 scandium. They are also known as twin radioisotopes or matched pair radioisotope. That means one will go for diagnostic purpose and another one will go for therapeutic purpose. Hence, the trust for present-day nuclear medicine can have three categories like search for non-standard PATE isotopes, search for new theranostic pairs, and search for alternative source of radioisotopes. The conventional medical cyclotrons, which give out this proton and alpha, they have certain limitations. So I would like to focus on the heavier activation and the high energy accelerators which can be used in production of these radioisotopes. Now if I come to heavier activation for production of non-standard PATE isotopes, then in the late 90s, several attempts were made by Professor Lahiri's group, and they were able to overcome the difficulties, and they were able to produce some of the radiolanthanides which are important in nuclear medicine. So I have given one example of thulium, which by proton-induced reaction can give 169 deuterium. But the problem here is that because of the similar chemical nature, the radiochemical separation is difficult. So how can this be removed? This can be overcome by heavier activation, where the target matrix, that is the radioisotopes, which is the target and the co-produced product is having the difference in the atomic number, and hence radiochemical separation can be easy. Using bar TFL electron, this group performed a lot of experiments where they have used 11 boron beam, 12 carbon beam, 16 oxygen beam or 7 lithium beam, and with the objective that they could produce some of the radiolanthanides which are important in clinical application, and they could also separate these co-produced products from their target matrix easily. If I give you some of the examples, then this is with the activation of 12C, where you can see several lanthanide targets, and you can see some of the daughter products which are medically important. Similarly, if I go for 16 oxygen beam, then there are also some of the daughter products which can be utilized for clinical application. Similarly, with the 7 lithium, 11 boron and 19 fluorine. Now, if they would have their own periodic table, then I think it might have looked like this, where several of the radioisotopes have been produced by heavy ion accelerator. And of course, there are some radiolanthanides and also some S&P block elements. The introduction of heavy ion beam made it rather easy to access the neutron deficient short-lived radioisotopes and expand the horizon of clinically important radioisotopes. So some of these radionuclides which are having moderate half-life, short or moderate half-life, and they have some intensity of 511 keV photopeak, they can be termed as non-standard PATE radionuclides. If I give you some of the example, then if I take the first example of cerium, then by conventional method we can produce 144 cerium and 141 cerium which have long half-life in days. But if we go through the non-conventional method, that is the alternative method, we can produce the non-standard isotopes like 135 cerium and 133 cerium having moderate half-life and can be used clinically. Similarly, there are many examples as you can see. And as I was telling you that 511 kV photopeak, yes, it is true that most of them do not have this intensity, but some of them does have that intensity, like 150 target, which is having a peak intensity, good peak intensity. So that can be used for clinical purpose. So this is one of the article which is going to be published in the Radiochemical Acta, which is basically on the production of neutron deficient rare earth radionuclides by heavy ion induced reaction. My second point is on the search for new theranostic pairs of nuclear medicine and the role of high energy accelerators. Yes, over the last 3 days, we have known CERN as, yes, it is known for high energy physics, it is known for God particle, it is known for LSC, but at the same time, it is also known for medical isotopes. As one of the article in CERN Bulletin in 2012 said, it published that CERN to start producing medical isotope. The project known by the name MEDICIS, and it is still MEDICIS, will make it possible to produce a large variety of radioactive isotopes for medical research. If I go to the map, then you will see that yes, there are many big projects like ALICE, LSC, CMS, etc. But there is also ISOLI, and CERN MEDICIS is the new facility which is coming, which is rather ongoing at present at CERN ISOLI, which is basically medical isotopes collected from ISOLI. That is, the medical isotopes are separated online. Why large facilities are becoming so important? Because of the reduced reactor facilities or shutdown of reactors and limitation of low energy medical accelerators. If I give one example of terbium, then 149 terbium is having a good half-life of 4.2 hours, and it is one of the few promising alpha emitter and can be used for alpha therapy. The production routes can be light particle-induced reaction, heavy ion-induced reaction, or by spallation technique. Due to low cross-section or very high contamination from other co-produced radioisotope, none of the either light particle-induced reaction or heavy particle-induced reaction are applicable. However, the spallation technique may be the only option which can produce this kind of radionuclides. This is another review that came up in the Frontiers in Nuclear Medicine, which talks about terbium radioisotopes, the pros and cons of producing terbium radioisotopes. Now, what CERN MEDICIS can do? They are producing different radioisotopes. They are doing the molecular engineering. They are doing radiochemistry, followed by pre-clinical research, quality assurance, clinical validation, and all. In short, quote unquote, they are doing what is called benchtop to bedside. That means they are doing all the experiments benchtop and the benchtop, and they are also giving the medical radioisotopes to the hospitals. Several hospitals in Geneva, in and around Geneva, are collaborated with CERN MEDICIS, where CERN MEDICIS program is regularly supplying medical radioisotopes for clinical purposes. Now, the concept of theranostic pair, as I was telling you that this is the present era of theranostic pair, actually I can take the example of terbium again, which is rather at present one of the most important radioisotope because of the quadruplet family. It is also known as the quadruplet family and also as the Swiss knife. Why Swiss knife? Because it can be used for various purposes. The radioisotopes, the 4 different radioisotopes, can be used for different purposes. Like it can be used for beta therapy, it can be used for alpha therapy, and also it can be used as PET and PET candidate. If I now talk about the 4 isotopes of 149 terbium, 152 terbium, 155 terbium, then you will see that 149 terbium is the sole alpha emitter which can be used for alpha therapy. 152 terbium can be used for